Yeah, so we discussed the work done by any force to be F dot D, the scalar product of the force and the displacement. And then we talked about the gravitational force and the work done by it, which is written as mgd cosine phi, or we said it can be written as minus mg delta h, because the gravity will, because it's always vertical, it will only do work when we have some vertical displacement. So today we're interested in one more force, which is the force exerted from a spring. So essentially, you have, let's say, a vertical spring, and there's a mass hanging from it. This spring stretches a little bit due to the hanging mass and exerts a tension force. This tension force is essentially upwards and is what's keeping this block from moving down due to gravity. So this block will be feeling both a weight force and a tension force. So this tension force, we also name it a spring force. And it has a formula. Just as the gravity is equal to m times g, a spring force can be defined by a formula, which is Fs equals minus kx, where k is the spring constant. It is essentially a constant related to how stiff or soft the spring is. So some springs are very stiff, they don't elongate easily, they will exert more force just from a little bit of displacement. So they will have a large spring constant, a large stiffness. And some springs are just soft, they will have a small spring constant or a small stiffness, and they elongate a lot just with a little bit of force. And my other quantity is what's written here as x, which is actually the elongation of the spring. The minus sign is written because the direction of the spring force is always opposite to the direction of the displacement of the spring. If a spring is elongated downwards, as you can see in my figure here, this spring is pulled down, it will exert a force opposite to this displacement, opposite to this elongation, which is going to be upward in this case. Why? Because the spring force is a restoring force. The spring always tries to restore its natural length. So it's going to be exerting a force which is opposing whatever you have done to it. If you stretch it, it will exert a pulling force to relax again. If you compress it, it will exert a pushing force to elongate back to its natural length. So this is what we also call Hooke's law. It's just the formula of the spring force exerted by a spring which is elongated or compressed. Now, we are interested in finding the work done by this spring. I defined for you the formula for the work done to be F dot D, right? The scalar product of the force and the displacement. But in this particular case, we will not be able to use this formula for the work done by the spring. So to find the work done by the spring, we will not be able to use W equals F dot D. Why? This is for a particular reason, which is related to the nature of this force. This force, the spring force, if you look closely at it, it depends on position. And because it depends on position, then as the block, let's say, moves across a certain displacement, the force it feels will be changing continuously. And then if you try to plug that here in our formula, let's say our displacement was 5 centimeters. Which force do you put over this 5 centimeter distance? Because F is minus k times x. So if you move 1 centimeter, F has a certain value. If you move 2 centimeters, F has a new value. The force is continuously changing. It doesn't have a constant value. I'm not sure which value to insert here. So what we have to do in this case, when the force depends on the displacement, we have to adjust our formula and change it into an integral. Use W equals the integral of F dot dx because F changes with position.
Professor?
So using our integral formula for the work done by a force that changes with position, I'm gonna find the work done by the spring force. So I know that the spring force, I'll just write for it, W is equal to the integral of the spring force dot dx. Now remember, this is still a scalar product, whether you write it as an integral form or as a dot scalar product already without any integration. It's a scalar product at the end of the day. So I'm keeping it as a scalar product. Now I want you to see something. We were told before that the minus sign here indicates that the direction of the spring is always opposite to the direction of the displacement. This means that Fs here and dx here, the displacement, are always opposite to each other. Fs and dx are always opposite. We discussed this before when we discussed Hooke's law, and we said this is because the spring always tries to pull back to its natural position. So if you elongate it, it will make a force trying to compress back to its natural length. If you compress it, it will make a pushing force in order to elongate back to its natural length. So since they are always opposite, then what can I say about the angle between them? Theta is equal to 180. And if theta is equal to 180 degrees, then cosine theta for the scalar product is going to be equal to -1. So Fs dot dx is equal to Fs dx and 180, which is minus Fs dx. So I was able to resolve the scalar product into some scalars, and thus my integral of Fs dot dx becomes an integral of minus f dx. Now I'll substitute the spring force by its expression, which is minus kx over here. I will not put the minus sign again. Remember, this was a vector expression. Once you talk about forces as magnitudes, as I did here, magnitudes are always positive. So I'll put minus kx. Let's look at our expression. I'll try to solve the integral. I'll take minus k to the outside of the integral. I'll have the integral of x dx. And this is none other but x squared over 2. So the solution to the integral will become minus half k x squared, where x squared varies between any initial and final position we are interested in. I will substitute x squared with x final squared minus x initial squared. I will expand this expression. You will get this formula for the work done by a spring. It is going to be half k x initial squared minus half k x final squared. This is the work done by a spring force. We can use this formula directly whenever we have a spring. We don't have to do this in the derivation. This is just for you to see. And one thing you will see here again, let's look at our equation. If x initial is larger than x final, done by the spring is positive. So if my spring was elongated a lot, and then I compress it a little bit, or it relaxes a little bit, then x final is less than x initial, then the spring will be doing some positive work, and the other way around. Let's check an example.
This meeting is being recorded.
So here I have this canister of mass m equals 0.4 kilograms. It slides across a horizontal frictionless counter with speed v equals 0.5 meters per second. And then it runs into and compresses a spring constant K equals 750 newtons per meter. When the canister is momentarily stopped by the spring, so this is basically at the maximum compression, here, by the way, V is 0 because we're told it's momentarily stopped. By what distance d is the spring compressed? So we're interested in finding the compression at this maximum compression case. So what I'm gonna do is I'm gonna write down my formulas. I know the work done by the spring force is equal to half K x initial squared minus half K x final squared. Like I told you, this formula, I will directly use it. I will not work through the integration. Now I know x initial. Okay, I have to select what my initial and final points are, by the way, right? I'll take my initial point to be here and my final point to be here. This is the final point. So I'm studying the work done by the spring force throughout the whole compression process. So what I know is at the initial point, the spring is not really compressed yet, right? So I can take this to be 0. X initial is 0, no compression yet at the initial point. So the work done by the spring force is none other but minus half K x final squared. Now x final here is none other but the distance d that we are interested in, and we're asked about the distance d by which the spring is compressed is basically the final compression of the spring. So this is the work done by the spring force. I know K, so I can write this as minus half times K, which is 750, times D squared. So what remains is to know the work done by the spring force by some means to be able to deduce D, which is what we want in this question. So to do that, I'm going to be using the work energy theorem, which says that the net work done on this canister is equal to the change in the kinetic energy of the canister. Now, the net work done is just the work done by the spring force. There's no other force doing work here because the canister is moving to the right, and thus the weight and the normal, they don't do any work because they are vertical, and horizontally all I have is just the spring force here when we start the compression. There are no other horizontal forces, and that's all. So W net is just the work done by the spring, which is minus half times 750 times D squared. Now, delta K is the change in the kinetic energy between the initial and the final points that I have selected. So this is K final minus K initial. Now, I wrote that at the maximum compression, V is 0. So at this final point, the speed of the canister is momentarily 0. It's at the maximum compression situation. So this is 0. And here I'll have minus half V squared. Now, what I still need is the initial speed. If I know this, I know the mass, I can solve for D. So let's look at our equation. I have minus half times, the mass is 0.4. What is V initial? It's the speed here. Well, the block started with a speed of 0.5 meters per second, and the floor is frictionless. So this speed will not really decrease with time. It will remain the same until the block reaches point I here and starts the compression. This is when it will actually slow down. So V is just 0.5 squared And let's look at our other side of the equation. You can see how D is now the only unknown. I can solve for D. I'll cancel these out first. Get D is 0.4 times 0.5 squared over 750 with a radical. I will solve for D. This is the maximum compression of the spring. You should get 0.012 meters or 1.2 centimeters.
This meeting is being recorded.
So we have discussed the general formula for the work done and the work done by some special forces such as the weight and the spring force. I have just one last comment on finding the work done by a force using graphs. So if we're given the force versus displacement graph, remember we talked before about how the slope of a given graph represents the quantity on the y-axis over the quantity on the x-axis, whereas the area represents the quantity on y times the quantity on x. For the fx graph, the area is going to be the force times the displacement, which is the work done by a force. So we can find the work done by a force graphically by finding the area under the fx graph. So I have this force versus x. From this graph, I find the area. This is the work done by this force. Quite simple. We have a nice application here. So we are shown the force versus position for an epidural needle. This is an anesthesia needle, which is used for childbirth. It's given through the skin at the back, all right, on the patient's back. It's a very delicate insertion, by the way, because the physician will have to insert it in a certain location between the bones of the backbones, you know. So we're told some details about how it's given and how the surgeon knows that they are at the right location to insert the anesthetic that they have to insert. So they just feel for the force as they go through the skin. And there's a certain location where the force is like less than the initial force, and then they know this is where they have to insert the needle. So anyway, we're given the variation of this force versus displacement at different locations as the needle is inserted. And the question was to find the work done by the force exerted on the needle to get the needle to the epidural space at x equals 30 millimeters. So we have a force versus displacement. We want to find the work. This is simply the area under the graph, right? So I'll just find the area under this graph. As you can see, our graph is a bit lengthy, but we're gonna do it anyway. I'm gonna split my graph into sections so that I can find the area of each section separately using the formulas we know for areas. And accordingly, after we find the areas under these sections, we can deduce the work done. So this is gonna be the area under the graph, which is basically the area under section A. Look how the graph already splits the graph into sections, plus the area of section B, plus the area of section C, plus the area of D, plus the area of E, plus the area of G, plus the area of H and F, and the area under section I, the area under section J, the area under section K. Let's look at each area separately, find it, and then we can add all of these up to find the work done by this force. Under section A, the area is none other but the area of a triangle. To find the area of this triangle, I'll use height times base over 2, which is the formula of the area of a triangle. How much is the height, here it is. It's this side, which is 12 newtons. How much is the base? Well, if this is 10, then, and I have here 5 blocks, so these are basically 2, 4, 6, 8, 10, 12, and so on and so forth. So the base is 8. Plus the area of section B, look at it, it's a rectangle. What's its area? It's just length times width, where the length is this side, which is 6 newtons, and the width is this side, which is 4 newtons. Plus the area of section C, here it is. This is also the height times the base over 2. The height is 12 minus 6, which is 6. This is our height. This is 6. The base is this, which is 4. We just found the area of section C. I will proceed to section D. Section D, I have the length is 6. D is basically a rectangle. So I'll do length times width. The length is 6. The width is, well, this is 18 and this is 12, so the width is 6 as well. Now, for the area for E is that of a triangle as well, so I'll do height times base over 2, which is, the height of E is this, which is, let's see, if this is 6, this is 12, then this is 7, this is 8. So the length of the height of section E is going to be 3. The base of section E is 18 minus 12, which is 6, over 2. Now I have the area of section G, which is a rectangle as well, so I'll use length times width. Section G has a length of 8 and a width of minus 18, which is 2. Section F is this tiny triangle here. It has a height 1 and a base of 2. And I have next the area of section H, which is a rectangle. Its length is this, which is 8. Its width is this, which is 22, 24, 26. This is 26. So this is 6. So we're studying section H, which is length times width only. I will not divide by 2. And I still have sections I, J, and K. I is a rectangle as well. So I'll put length times width again. So for section I, the length is 8. The width is 2. For section J, I have a triangle. So this is height times base over 2. The height is, so I have 4. Yeah, this is 4. Times the base, which is 2 over 2. And finally, I have section K, which is a rectangle. This rectangle has a length 12 and a width of 2. You calculate all of these, you add them up, you should get 0.24. And remember, the unit of the work done is joules.
This meeting
Our
is being recorded.
last section for this chapter is related to how fast we do the work done by a force. So we talked about the work done by a force, but the rate at which the work is done is also an essential quantity. Because if you work faster, then you're spending a lot of energy in a shorter time. This means you have more power. So we're defining the power as the rate at which the work is done by a force. So this is basically, whenever you see the word rate, by the way, in physics, this means we are checking the variation with respect to time. So the power is the rate of the work. This means it is the work divided by the time. So this is the definition of the average power of a certain force. It's the work and how long it took us to do this work. We can check the instantaneous power. It will be just the derivative of the work with respect to time. The SI unit of the power will be joule per second, as you can see, which is what we also define as watts. You might have seen this if you've taken any electricity study where we find the power of a certain electric circuit or a certain appliance in a circuit, and this power was measured in watts as well. Now I have this nice derivation of the power as well in terms of the force, rather than writing it in terms of the work done. I know the work done itself is F dot X, right, or F dot D. Because the power is dW by dt, the derivative of the work with respect to time for the instantaneous power, I can substitute W by F times cosine theta times dx, because it's a dW, some infinitesimal W. Let's look at dx over dt. This is none other but the velocity. So I can substitute this quantity here by the velocity v. Now, this is a scalar product, so I will have to write v as a magnitude, not as a vector. I will end up with a new formula for the power, which is f times cosine phi times v. Look at it here. This is f v cosine phi, and this is actually the dot product between f. So the instantaneous power can be either written as dW by dt or as F dot V. You use either formula according to what you're given in problem solving. You can check this example here. We have two constant forces, F1 and F2, acting on a box as the box slides to the right across a frictionless floor. We're given the magnitudes and directions of the forces. We're given the speed of the box at a certain instant to be 3 meters per second. The question is, what is the power due to each force acting on the box at that instant? So I want the power of each force at that moment. Because I'm given the velocity rather than the work done, I'm going to use the power to be F dot V, which is F times V times cosine phi. I'll simply write the magnitude of the force, the magnitude of the speed, and the angle between them. So the box is moving to the right. F1, look at it, it's completely to the left. So the angle between F1 and V is going to be 180. So here I'll put 180. Whereas for F2, F2 makes an angle 60 with the horizontal, and V is along the horizontal. So the angle between F2 and V is also 60. So for P2, the power of the second force, this is going to be F2V cosine 60. And you solve for the power. We can find the total power. If we want, what is the net power? Yeah, we are asked for the net power. I'll just sum these two. The power is a scalar, so I add it numerically. I don't have to worry about x and y components. So with this, I finish chapter 7, and this was basically covering work done by forces and the energy involved when we exert some forces. In the next chapter, we're going to be talking about some stored energies that a body can convert into motion. And these stored energies are also exerted by particular forces, which we have studied before in chapters 5 and 6.